Welcome, this is Professor Nathan Weezy of Marquette University. This section we're going to talk about the current mode control of a buck converter in section of digital control power electronics. In this one we'll specifically focus on the design of the continuous time controller, and in subsequent sections we'll actually convert that to a digital controller and check its response. So let's just briefly talk about the current mode control structure. In black here in this diagram you see that we have a buck converter, and I can go ahead and label certain components like LC, the load capacitance, and the capacitance ESR. And in blue here we have our control structure. So for example, we'll measure the output voltage and we'll subtract from that the reference and generate an error. That error will be fed into our controller. That controller will generate a command for IL. And we'll actually measure the current and compare the two. Whenever IL actually reaches IL star, we'll generate a small little pulse here. And this here is a simple SR latch. And this signal right here is essentially our set signal that happens at the switching frequency set at FSW. I can sketch out how this actually works to get a better idea of what's going on here. So we'll look at the S, the R, the Q. So the S and R are the set and reset inputs of the SR latch, and Q is the output. And we'll also look at the three signals coming from the op amp, which is IL and IL star. So the first thing that happens actually is this block down here generates a fixed frequency small set signal. So this will happen at FSW. So we'll call this TSW, the switching frequency. And what it does is it just turns the switch on right at the time. So as soon as it hits 1 at the beginning of the cycle, Q turns on, and that's going to happen every cycle. And this is a really thin pulse, say maybe 1% of the duty cycle or less, and it's just generated. It's a pulse, continuous pulse spectrum. Now what happens is as soon as you turn the switch on in a buck converter, actually the current ramps up. It'll ramp up to some point, and we'll have this line here. In green here, we'll call this line IL star, what we want the current to be. So this is IL star, what we want it to be. And blue is what it actually is. And what will happen is, they'll keep going. This comparison here, the output of this comparison will be 0 until IL actually hits IL star. So as soon as they hit, say right here, guess what? We generate a switching signal at the output of our comparator, which is actually the reset. So you'll see this little pulse be generated. And what will happen is Q will now, boom, go straight down until the end of the cycle, and then where it gets set again. And this cycle will go on and on and on. Now watch, once you turn it off or you hit a reset signal, the current in a buck converter goes down. And of course at the start of the cycle, the set is generated by our pulse spectrum. That'll set it again. The current will ramp up until, boom, right about this point, the two match, and you'll generate a signal at the output of your comparator, which will generate a reset, which will bring Q down low again. And again, the current will ramp down. And this goes on indefinitely. So you can see very simple with an SR latch, a comparator, and this pulse generator here, this continuous pulse generator. You could generate a very simple, crude current controller. Now, what this does is just, if you ask for IL star, it makes sure the peak is at IL star. Now, what we have to do is design GC of S. What should IL star be such that there's no error, or in other words, that our output voltage matches our reference? Okay, now, equation 1 here is our plant. This is generally reserved for a Intro to Power Electronics course. This is generally derived there, and this is a plant for the buck converter in CCM. Let's talk about some of the values here. C is the output capacitance, capacitor. This is the capital R is your load resistance, and your small r is your ESR, or the capacitor's equivalent series resistance, aka small r. Okay, and then let's see. That is the small signal transfer function from IL to VO. So it's a small perturbation IL to the output voltage. And we're going to use the plant to design a controller. We need to know how it responds. Now, one thing you can note here is that it has 1, 0, and 1 pole. And this is different than voltage mode control. So this should, in general, have a nice a single pole response, which is nice, or a first order response, if you will, instead of voltage mode, which will have a second order due to the nature of the plant. These are the parameters that we're going to use to talk about in this section. Again, this is similar to voltage mode: input voltage of 30 volts, output voltage of 15, inductance of 200, capacitance 400 microfarad, ESR 1, load resistance 5. This should give you at full load IO of 3 amps and an output power of about 45 watts at full load. And lastly, our switching frequency would be 100 kilohertz. So what we're going to do is go ahead and plant the or body plot the plant. So this is our plant of our body of our plant. And what you see here is that actually, if you look over here, I have it for 3 different variables. What I'm doing is sweeping the load, or the load resistance, from 1% to 100%. So 100% would be 5 ohms, that's full load, and that would actually be this blue line. And then 1% would be 1% of the full load. So in this case, resistance goes up as the load goes down. So think 500 ohms, that would be this one up here. So you can see this, this moves the gain, the DC gain. Doesn't really move the pole, well, it does move the pole, but moves the DC gain up and down. But that's to be expected because this is really the impedance. It's I to VO. And as R is going up and down, you would expect the DC gain to move. And the other thing, if we go back and look at the plant briefly, if we're changing R, what we're actually doing is moving the pole. You can see it right here. So like, for instance, the pole at light load is here, the pole at like 10% load is here, the pole at 100% is here. These are the pole locations. And it does move on you. So you kind of want to keep that in mind when you're designing this control loop. And of course, since the pole moves, you can see the phase plots moving here, depending on what the load is. All right, let's try to design a controller for this. What we're going to do is do the K-factor approach, but since we have a single pole and 0 in our plant, we're going to use a single pole and single 0 in our controller. So you can see there's not a squared term in here. So a pole 0, and of course we want 0 steady state error, so we have an integrator. And again, our goal is really defined for the controller design, just these 3 parameters, the gains, K, omega Z, and omega P. Once you have those, essentially your controller design is complete. Now what we're going to do is the same type of approach. What we're going to do is pick a desired phase margin and bandwidth. So we're going to pick phase margin and bandwidth. And let's see what did I use for this FC. So that's essentially how fast the system responds. Once you do that, similar to the voltage mode design, you want to get the gain and the phase of the plant at the desired crossover frequency. And we'll run through this with our MATLAB script here in a second. Once you have done that, you take your desired phase margin and the phase of the actual plant at the crossover frequency, subtract 90, and this essentially tells you how much phi boost you need from your controller in order to have the phase margin you selected. Then this will give you this next equation, which is equation 7, will give you K boost factor. This is the ratio between the pole and 0 location. Essentially, this will make sure that you place the poles and zeros such that you get the amount of phase boost. These next 2 equations, 8 and 9, once you have K boost, will give you your 0 location, your pole. And then this last one is the gain of the integrator, or K, the gain of the controller. So it's a pretty straightforward process, very similar to the voltage mode design, with only one major difference. It's here in the K boost. Since you only have one pole and one zero, in order to get the actual ratio, you divide phi boost by 2 and not 4. Let's walk through this in terms of the design from the script. But before I do that quick, what did we want to design for? In this example, I went for 1 kilohertz. So 1 kilohertz should be about here on the plot, and you can see where I'm designing it. It's not really a function of the load, at least from 1 to 100%. This point's really not moving around, so we'll take a look at see what happens with that later. And the phase moves a little bit, but that's okay. You can see essentially at really light load we'll have less phase margin than we will at heavy load. Okay, so we're going to go ahead and design this. What we'll do first is get the gain and phase here. I'm just kind of going to eyeball this. This looks to be approximately minus 10 dB, very roughly eyeballing it. And if we're looking at the blue line here, let's see, what do we have in there? 45. It's a little bit lower, approximately 70 degrees, minus 70 degrees, let's call it. Okay, so we're going to run this script. Here's our buck parameters from MATLAB. I'm going to implement these equations now. Here's our desired controller parameters. In other words, bandwidth, phase margin. So you get to select these. 13 and 14, that's going to get your gain and phase of the transfer function of the plant at the desired crossover frequency. So gain and phase of plant, and then essentially 16 and 17 will give you the gain that you need from your controller and the phi boost you need from your controller. And these are now our controller gains. We can calculate those directly. We get our pole, we get our zero, and we get our integrator gain. And that should actually be all the way down here. So I have FC and omega Z. I have it in radians or hertz, depends on what you like. And if you run this for this design, what you'll get is about 2,800 radians for the zero. So you can see the zero happens first in terms of going from DC up in frequency. Then the pole's at about 1,400 radians with an integral gain around 7,000. So let's check our controller again. We designed this at 1 kilohertz. And so the gain we got is somewhere around 10 dB. Remember, our phase of our plant was minus 10 dB. So you can see that at the crossover frequency, if we add these two together, we get about 0 dB, which is a gain of 1, which is exactly what we wanted. We also see here our phase margin, or the phase that we're adding here, kind of ballpark this, minus, let's see, this is 30 degrees. Let's say this is minus 50 approximately, somewhere in there. So we're going to subtract 50 degrees of phase actually from the system. And you can see, if we minus 50 from minus 70, you're at about minus 120, which gives you a phase margin of 60. So this is looking good. If we now look at our open loop, so you multiply the two together, you can get exactly what I was saying. You look here at 1 kilohertz, the gain crosses through 0 dB at 1 kilohertz, and our phase margin is, looky, minus 120 degrees right at 1 kilohertz. So that's looking good for the open loop gain. If we go ahead and close loop the gain, this is what we get. You can see we have a nice flat 0 dB gain with a little bit of a hump here, a little bit of gain, and then we shoot down at minus 20 dB per decade. So we're looking good for the closed loop response. You could probably do a little bit better, try to dampen that a little bit better, but this should be a pretty decent response as is. So let's go ahead and simulate our controller here for 1 kilohertz with a continuous time controller. We're going a 10%, so this should be 10% up to 100% in terms of load current. You can see the voltage was at 15, dips down, the controller starts actuating, and we come back up and we recover. It takes about, if you go here, 1 millisecond approximately. Remember, we're at 1 kilohertz, so 1 over 1 millisecond is 1 kilohertz. So it kind of gives you a rough approximation of how fast your controller will respond. You can see the current jumping up to here, and it does overshoot a little bit, and again, that's because we don't have perfect damping here. If you could get this design here damped better, and we could do that back up here. Something that's kind of getting in our way here is you see this dip here in phase. So we can move our controller back or move the zeros and poles up in order to deal with that. Make that a little bit better in terms of the closed loop response. So you can move this stuff around, play with it, and then you also don't have to do the K-factor approach. You could arbitrarily place your zero and pole to get a better response, and all you want to do is essentially shape this open loop gain to your desire. So for instance, if I were just to arbitrarily place the pole and zero and not do the K-factor approach, what you'd really like to do is kind of shape the phase so that maybe you don't go down here like this. So if you could keep it up somewhere like this, and then shape your open loop gain to cross through your desired bandwidth, you'd have a little bit better damped response than we currently have. Okay, and you can do that graphically, or you can start to write some equations that are to do it. So what happen with the K-factor approach is you have one constraint that you're adding, and that's that the geometric mean of the pole and the zero are centered at the crossover frequency. But if you relax that constraint, you're no longer doing K-factor approach, which means you basically have a third degree of freedom. That means you can place the pole or zero wherever you like. And then you can do the loop shaping kind of almost manually. Okay, this concludes this section, which is on the design of a current mode controller for a buck converter. Thank you.